Welcome, everyone. Today, we're diving into Problem 12 from the 2025 Gaokao, exploring parabola rotations and how they intersect with lines. Welcome to this problem session where we tackle Problem 12 from China's 2025 college entrance exam known as the Gaokao. Let us read the problem carefully. Part 1 asks us to find the distance from the focus to the directrix. This requires us to first determine the parameter a using the given point.
And part 2 involves a rotation. We rotate the axes counterclockwise by 90 degrees around the focus.
Then we need to count how many times the line 2x plus y minus 1 equals 0 intersects with this rotated parabola g.
So we have two tasks. Find a distance in part 1 and count intersection points in part 2.
Exactly. Let us start by reviewing the basics of parabolas before we dive into the solution. Before we rotate anything, let us recall how a standard parabola, its focus, and its directrix are related. In many problems, we meet the basic sideways parabola, where y squared equals 4ax with the vertex at the origin. For that curve, the focus sits a units to the right on the x-axis, and the directrix is the vertical line, the same distance to the left.
So every point on the parabola is the same distance from that point at a comma 0 and from the line x equals minus a, right?
Exactly. Today, we will take one of these parabolas, rotate it about its focus, and then see how many times it crosses a certain straight line.
Got it. So if I remember how focus and directrix work, the rotation part will just be a new twist on that picture.
Here is the full problem statement we want to unpack step by step. First, the parabola is of the form y squared equals px, and we are told that the point 1, 2 lies on it.
So step 1 is basically to fix P and pin down the exact parabola plus its focus and directrix.
Yes, once we know P, all the geometry of the standard parabola follows. Then we imagine rotating the parabola 90 degrees around its focus while the coordinate axes stay put.
And finally, we want how many points that rotated curve shares with the line 2x plus y minus 1 equals 0.
Exactly. We will turn that geometric question into a quadratic equation and read the answer from its discriminant. Let us start with the basics, using the point to determine P and the focus directrix setup. We begin by using the point to find P and then reading off the focus and directrix from the standard form. Plugging in x equals 1 and y equals 2 gives 4 equals P, so P must be 4. So our concrete curve is y squared equals 4x, the classic right opening parabola. Comparing with the pattern y squared equals 4ax, we see a is 1, so the focus is at 1, 0.
Because the focus moved 1 unit to the right, the directrix should be the line x equals minus 1 to the left, right?
Exactly. The directrix stays the same distance from the vertex, but on the opposite side. The focus is at x equal 1, the directrix is at x equal minus 1, so they are 2 units apart.
So the original parabola and its focus directrix setup are completely fixed now.
Next, we want to understand what it means to rotate the parabola 90 degrees around its focus. Think of the focus at 1, 0 as a pin in the paper that we rotate the curve around. Rotating the axis counterclockwise is equivalent to rotating the curve itself clockwise by 90 degrees, while keeping the axis fixed.
So the line grid stays put, and the parabola swings around the focus.
We can follow an arbitrary point on the original parabola and write a formula for where it lands after that rotation. Relative to the focus, a clockwise quarter turn sends the vector from x minus 1, y to y, minus the quantity x minus 1, so the new coordinates become 1 plus y and minus the quantity x minus 1.
So the old x-axis direction becomes downward, and the old positive y direction becomes to the right in the rotated picture.
Now that we have the coordinate mapping for rotated points, we can turn it into an equation for the whole rotated parabola. Let us convert the geometric rotation into an algebraic equation for the new parabola. We start from the original relation between x and y, namely y squared equals 4x. We invert the rotation formulas to write y as x prime minus 1 and x as 1 minus y prime, then plug these into the original parabola equation and simplify. So in the rotated picture, the new coordinates satisfy the equation, open parentheses, x prime minus 1, close parentheses, squared, equals minus 4 times open parentheses, y prime minus 1, close parentheses.
That looks like a vertical parabola with vertex at 1, 1 opening downward.
Exactly, the squared term is in x prime, and the coefficient in front of y prime minus 1 is negative, so it opens down. Because we rotated around the focus, that point remains fixed at 1, 0 for the rotated parabola. From now on, we will drop the primes and think of this rotated parabola as having equation, open parentheses, x minus 1, close parentheses, squared equals minus 4 times open parentheses, y minus 1, close parentheses in our usual xy plane. Now we are ready to combine the rotated parabola with the given line. In our usual coordinates, the rotated parabola satisfies open parentheses, x minus 1, close parentheses, squared equals minus 4 times open parentheses, y minus 1, close parentheses. The line has equation 2x plus y minus 1 equals 0, which we can rewrite as y equals 1 minus 2x.
So to find intersection points, I should plug that expression for y into the parabola equation.
Yes, that will produce a single equation in x whose solutions correspond to intersection x coordinates. After substitution and simplifying, the condition for intersection becomes a quadratic equation in x. Carrying out the substitution, the y minus 1 term becomes minus 2x, so the right side is 8x, and simplifying gives the quadratic x squared minus 10x plus 1 equals 0.
So now the number of intersection points is just the number of real roots of that quadratic.
To finish, we evaluate how many real solutions that quadratic has. For the quadratic x squared minus 10x plus 1, the discriminant is 10 squared minus 4 times 1, which is 96, a positive number. A positive discriminant means the quadratic has two distinct real roots for x.
So each x value from that quadratic corresponds to one point where the line and rotated parabola cross.
Therefore, the rotated parabola and the line meet in exactly two distinct real points.
Nice. We did not even need the exact coordinates of the points, just the discriminant to count them.
Let us step back and connect the geometric moves with the algebra we used. Using the point 1, 2, we fixed p as 4 and identified the original parabola as y squared equals 4x. From the standard form, we knew the focus was at 1, 0 and the directrix at x equals minus 1, 2 units away.
Then rotating around the focus turned the sideways parabola into a downward one, with equation open parenthesis x minus 1, close parenthesis squared equals minus 4 times open parenthesis y minus 1, close parenthesis.
Finally, intersecting with the line 2x plus y minus 1 equals 0 led to a quadratic with positive discriminant, so exactly two intersection points. A handy exam tip is that rotating the coordinate axes in one direction is equivalent to rotating the curve itself the opposite way about the fixed point.
It is cool how a geometric move like rotation turns into a coordinate substitution and then back into counting roots.
Let us check your understanding with one more quick rotation question. For practice, imagine the parabola y squared equals 8x. Its parameter a is 2, so the focus is at 2, 0 and the vertex at 0, 0. Rotating 90 degrees clockwise about the focus moves the vertex 2 units above it to 2, 2, making a downward opening vertical parabola with equation, open parentheses, x minus 2, close parentheses, squared equals minus 8, times open parenthesis, e minus 2, close parenthesis.
For me, the rotation mapping was the trickiest part because I had to picture how the coordinates move around the focus.
That is very common. When you review, try sketching the axes and the focus, then draw how one sample point moves under a quarter turn to make the mapping feel concrete. Once the rotation picture is clear, the rest really is just quadratic algebra and using the discriminant. Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback. Leave questions and suggestions in the comments.